Okay, good afternoon, everyone. My name is Amit Ghoshal, and I thank the organizer for this opportunity to present our work. So the title of the talk is "Emerging Inhomogeneities in Non-Equilibrium Superconductors," and this work is done primarily by Medha Roy Choudhury, who actually the PhD student who put the work to progress the project. We benefited a lot by a very active collaboration with Professor Pinaki Mojumdar, who was at HRI when we started, and then now he's in Ahmedabad University, as well as we benefited from significantly from the involvement of Shankar Subra Bakshi, who was a PhD student at HRI, and then before moving to Virginia, he was a postdoc in IISA Kolkata for some time. Okay, so today we are going to talk about quench. So what is a quench? So it's a time evolution of a system whose parameters are drastically changed. That's the simple definition of quench, and it's a very popular thing in classical statistical mechanics where people talk about phase ordering kinetics. So what you do is you take a paramagnet which is at a high temperature and suddenly quench it to a very low temperature, like zero temperature, and then you ask how the little puddles of up and down spin evolve to make a cluster of large size as it approaches equilibrium. So we have in JNU one expert, Professor Sanjay Puri, who has been contributed significantly in that field. But we are not going to talk any more about thermal quench, but we'll talk about quantum quench. So where one does, for example, so in quantum quench one talks about coherent many-body dynamics. So you take a superconductor. There is not a quench across a phase, so you take a superconductor with some UI. UI is the superconducting attraction. I mean, we'll define things more as we go along. So which is giving you some superconducting pairing amplitude delta I, and you suddenly put the value to UF, and corresponding delta F will be the equilibrium delta for that system at UF. So the questions you ask is, how does the system evolve in time? Where does it end up? Does it equilibrate and all that? And the answer depends on the Hamiltonian, which is controlling the dynamics, as well as the initial conditions. There are a possibility that it will equilibrate at some effective temperature. There could be a possibility that there will be just an asymptotic steady state and with phases, new properties, and so on and so forth. So the goal here is to ask when and how does a dynamically generated homogeneous superconducting state become unstable to a spatial structure following an interaction quench. Okay, so to elaborate a little bit, the attractive Hubbard model, which we'll be defining, but most of you know what that is. So attractive Hubbard model, if it is subjected to an interaction quench, it of course admits a homogeneous post-quench solution wherever the initial state is homogeneous and the Hamiltonian which is evolving it is translationally invariant, which is the case for us. And we are going to develop an understanding for dynamic instability and structure formation in a self-generated non-stationary background. That is the one that I just referring to. Okay, so let's start with what we know about the systems. So early works for when people studied homogeneous dynamics, one starts with a Hamiltonian like this. Is just the BCS Hamiltonian, but one considers these deltas as time-dependent fields, and then one develops the Heisenberg equation of motion in terms of this mean field Hamiltonian, considering the two fields, which is essentially density and anomalous grid function. And total delta is defined as this will be F should be K here, sum over all F of K, and that's the definition of delta. Right? So this leads to a coupled equation for F and G, and then you solve it, and thereby you get the dynamics. And if you look at the result of delta T, meaning the time dependent delta, so the time behavior can be classified in broadly three regimes. One is persistent oscillation like this. This is for delta I by delta F, which is essentially the quench strength. Which is very small. This is something intermediate where you see damped oscillation, and then there are other cases where you can have over damped oscillation. But all the time the system will remain homogeneous. So that's the background homogeneous time dependent field that we have in mind. So now we consider something more. So we consider Let's say we make a weakly inhomogeneous initial condition like this, so that delta naught is the one that I just talked about at the initial point, some homogeneous equilibrium solution, and then you give a very small perturbation eta I. So where eta i's are very small. So the subsequent time evolution, you can write this delta I as a function of t as something which is the homogeneous solution as a function of time, the oscillating part that we talked about, and some additional piece. So now the question we'll ask is, does an arbitrary small perturbation eta I can make this thing to grow or decay under time dependent background provided by delta naught t? That's the question we'll be focusing on. Okay. So if the final result is all the perturbation remains bounded, then the homogeneous trajectory is stable and the system remains essentially homogeneous, probably with some weak inhomogeneities. If some perturbation grows exponentially, that's the instability, and the homogeneous trajectory will become unstable to spatial structure formation. Okay, so now what is the instability? Instability is the following, that how to identify instability. So we start simulation with a configuration of local delta and rho consistent with an equilibrium solution at ui at t equals 0, in presence of a very weak inhomogeneity, extremely weak inhomogeneity of the order of 10 power minus 8. And we do that purposefully to see if the homogeneous solution that we just discussed is stable to such a perturbation or not. So the identifier is something like eta, which is the spatial variation of delta given here, divided by the average delta. So this guy, to begin with, I mean, I had some eta which is put in by hand, some inhomogeneity that is very small. So does it remain that small, of that order that we start with, or does it grow? So if it grows like that exponentially, that will be an instability, and we will address if there is an instability, what are the effects in various physical observables. Or does it remain 0? That's a possibility. Then it's just a homogeneous solution. That will mean that the homogeneous solution is stable. And even if it grows very slowly to some value which is not its strong, so there could be such possibilities, that will not be called at least instabilities. So what turns out, if you look that if you do the actual simulation, what you see is something which is quite remarkable, that in every possible perturbation that we looked into, so I'll explain this plot first. So these are URs. URs are defined as, I forgot to mention that, this is a dimensionless parameter for the strength of the quench. So that is UI minus UF divided by UF. So this is a dimensionless object, and that of course gives you the strength of the quench, and that can take a value positive and negative both depending on which one is larger and which one is smaller. So what we are plotting here as a function of time, the behavior of this eta as a function of time. Time is given in terms of some fundamental time scale, which is 1 over hopping of the Hubbard model. We'll come to that again, but this is essentially time. So as a function of time, every set of parameters that you see here listed, we have an instability, in the sense that this remains 0 for some time and then suddenly goes up. Finally, it comes down at a longer time. That's a different thing. But in every case that we listed here, there is an instability. And this is true for both UR being positive and UR being negative. So what happens if you focus this side? For example, in this case, this is a strength which is minus 0.4. Minus is not important. It just says that which one is larger of UI and UF. So that is that instability occurs at a time which is small compared to if it is when UR is small, like 0.23, the instability will occur at a much larger time. And also the instability is stronger here, the strength of instability, than the other case. And this is typically true for all data that is here. I will not try to explain all of them, but this is something to keep in mind. So of course there is a possibility that you can go to a very, very small UR, and then the instability, you may not see the instability that might occur at a very, very large time that is beyond the scope of simulation that we carry out. Okay. So now, given that I talked about the basic structure or basic terminology of my talk, it's time that I give you the outline for the rest of the talk. So first I will talk about the formalism for comprehending dynamics in the superconductor after quench, the one I discussed. The dynamical behavior of the superconductor after an interaction quench will be classified in different different temporal regimes based on the behavior of the global superconducting order or some other observables. We'll list them. We'll calculate the time scales, etc. Those are standard thing to do. This is again a mistake here. And we'll carry out the analysis of emerging inhomogeneities. So what is very important, and that's what we come to in the end, that this occurrence of instability is intimately connected to emerging inhomogeneities in the system. So that's the part which will be discussed here. And then we'll ask whether is it an instability or is there some spatial structure, something which is evolving, some length scale that is evolving, or domain formation and so on and so forth. I mean, we'll do a little bit more with the space inhomogeneities. So first, it's a very, very busy slide, but because we have seen another, so we are brave, so we can put it up and just look at the relevant portion. One thing is that we are working with attractive Hubbard model, which is our model for superconductor. That we have already said. And then we will be working actually with a mean field version of it, mean field decoupled equations, and then with that we'll evolve the Heisenberg equation, which is all like before, except for the fact which is very important, that we'll now develop things in real space, not in momentum space, because as I said that the instability might be connected to development of inhomogeneities and all that. So we'll develop everything in real space. And our field that we'll be following are delta ij and rho ij. Okay, rho ij is the density and delta ij are the pairing amplitude, but you have to understand, you have to focus on this, that these are delta ij. So it is, I mean, all delta ij for all I and j are taken as dynamical variable. Okay, so consistent with the fundamental symmetry of the superconductor, whatever you might have. So in some sense, this is something which is not done in the momentum space calculation. You don't consider delta kk prime the kind of term you have, for example, when you talk about FFLO physics and so on and so forth. But these are included here. And this will lead to then some coupled equation, which is very complex, but I just show it just to say that we did it. And we list the observables that we investigate. Yeah, this is the thing that I was telling you that time, that the time is measured in terms of the unit, in the unit of tau naught, which is 1 over t hop. Th is t hop, hopping of the Hubbard model. We will be following the behavior of superconducting structure factors, which is the standard structure factor. This will be like delta square, delta at k equals 0 mode of that. So how does that evolve with time? Remember that in our formalism, this allows for phase fluctuation in the system, which is not there in the homogeneous theory, because it's a homogeneous theory that you can show. So we'll have phase fluctuation, so we can study independently the delta I amplitude as well as the phase of it. So we'll also be looking into the charge order structure factor, or CDW structure factor, if you want to call it that way. So, and we will particularly look into the pi mode, because that's the one which is very dominant, close to half filling, if you so wish. I mean, this is, sorry. And then we will be looking into the bond currents, which are defined in standard way. Again, I draw your attention that these are not available in the homogeneous theory. You can look at the current because they can be generated. There cannot be a global current, but there can be local current which will be cancelling each other, and we'll see that. So yeah, so this is written here that Jx and Jy is 0. So all current that you can have is the RMS current, some current fluctuations. Okay, so now let me come to the some of the results. So far I have been talking about the instability and classifying them in terms of sigma of delta, the standard deviation of delta. So here what I show is the structure factor itself, and this is a situation. This is a set of parameters which are like here, and which will be falling into regime 1. I will explain what that is. where this thing makes a complex oscillation towards the early time, and then there's a pinching of the amplitude of the envelope of the amplitude of the oscillation of this term. Okay, so that is something which is shown by this dotted line here, that there is a narrowing, I mean, which is sort of obvious here. So early times you have complex oscillation. By that it's a multi-frequency oscillation. That's of course possible in our case. That is not very hard to see, and that will give pronounced beating features and all that. And then what turns out also interestingly, that in this regime, in this particular case, that as soon as, this is something which is more generic, and I will talk about that more, that whenever there is this pinching occurs, the time scale for the pinching of this thing, and that's where the instability occurs, the instabilities that I had shown, and that's the time there is this RMS current that grows in the system. Okay. Okay, so that's, and this is we call regime 1 of dynamics. Regime 1 of dynamics is defined in terms of the fact that this oscillation, this is of course not here. Of course, by the way, I should make it very clear that these oscillations are oscillations in time. The spatial quantities are completely homogeneous up to this point until it hits the instability or this pinching that I talked about. However, what it turns out that this S of SC, actually this is plotted SSC, the structure factor, normalized by the structure factor value at the UF, the final value of U. So that thing remains constant. On an average, there is no change in this value, the average of that, the smooth part of that. So that basically what qualifies it to be regime 1 of dynamical behavior, and this should be contrasted with the other regime where the quench is stronger, as the number would say, compared to this value. This is larger. And what happens is that here what you see, initially it will appear seemingly a persistent oscillation for some time. However, this is very violent oscillation as a function of time, but spatially delta will be completely homogeneous until a point where there is an almost collapse of the value of SSC, and then there will be a revival at a very long time scale and very slow and gradual revival. And it comes to a value, because this thing is actually normalized in terms of the value at the equilibrium at final U. So that value is much less than 1 wherever it is going to. Okay, so that is your regime 2, and so these are written here that SSC reaching only 60% of the equilibrium value. Again, I just draw your attention to the fact that whenever it is collapsing or near collapsing, the current grows in the system, which was 0 until that point, or nearly 0 until that point, and this actually coincides again with the instability that I have talked about in terms of sigma delta. Alright, so now in this way we can look at various different points in the space of UR or UI and UF plane, and then what we can do is draw a phase diagram where the diagonal line, which is UI equals UF, this is a homogeneous solution. There is no dynamics because there is no quench at all, right? That's sort of an obvious line. Now, far from it, you have different behaviors. The behavior which I called the collapse and then revival, which is the regime 2, this one, so this thing goes down and comes up, that leaves in this phase, this leaves in phase diagram only in this regime. This is the regime 2, and then rest of the space is regime 1, except for the white band. White band is the regime where we can't really, this is something which is inaccessible to the numerics, because the system does not show any onset of instability up to the longest time of our simulation. Whether it will be coming or not, we don't know. It could be either homogeneous or something that we don't know. So this is inaccessible, but very large, the main thing where I want to draw your attention is for very large parameter space, the homogeneous dynamics is unstable to any small perturbation, or particularly they all lead to instability. So the color shading is something that I will talk about. The color shade represent the time scale for the onset of instability. So smaller the value of u r, I mean basically the difference between the two which is close to this around the diagonal, there the time scale wherever it actually emerges is very large, and that is what I showed you in the very beginning, that the instability occurs but only at a very, very large time. So that time scale, that's this darker line, and then as you go away this is more white type or yellow, whatever the color is. So that is basically, this is identified based on the time scale for the instability to occur. So there is a very large window where the system is rife with instability. That's the way I will say. So now the next part that I wanted to tell you about is that, okay, so now what I go back a bit. So either of this case, so what is the asymptotic value at a very large time? So this we have analyzed by doing an appropriate fitting, or what is the value of delta at the, I mean it is not delta, the SSC, the structure factor at infinite time. And what I plot here is that value SSC. Now I have put this SSC 0, which is the normalized by the value at equilibrium with the UF, the final U. So there you can see that the behavior, I mean this is, of course, this has to be oh yeah, 10 power minus 1. So this is 1, this has to be 1, right? I mean, because this is exactly the same value. And then as you go away from the equilibrium value, either positive side or negative side, this decreases. And it seems also interesting that here I have put data for 3 different values of UF, but URs are matched for all cases. So it's not so significantly dependent on UI and UF independently, perhaps, at least to the extent they seem to fall not on the line but in a band to that extent. Okay. So now this is, I just wanted to quickly tell you that while the instability is interesting and I have been talking a lot about them, what is also interesting that how the system behaves beyond the instability, and it seems that the sigma delta actually decreases beyond the onset of instability gradually, very, very gradually. What is even more interesting, or at least as interesting, is that not only does it decreases, it never goes to 0. So the system has an inhomogeneity, however weak it is, it persists until very large value, it never comes down to 0. Okay, and the residual value is larger for the regime 1 or weaker quench than for the case of the stronger quench that I talked about, regime 2. This inset shows about the inhomogeneities in the distribution of deltas, but that is sort of included in this one. However, I mean, beyond there is an instability, you have to trust the numerical result because the systems are very, very nonlinear and very hard to solve any other ways. So now for the last about 5-7 minutes, 2 minutes for 30 of.
No.
Okay. So then maybe I will focus only on one part, and then I will. I mean that will probably do my job. So now the question is, whatever I have been motivating is what is the nature of inhomogeneities because of this instability. So what you see, the system is homogeneous in the sense that here I show the delta amplitude, here is the phase, and then here there is a S of k, which is the Fourier transform of this delta. So here you see it's completely homogeneous, and suddenly whenever there is an instability, large structure come in, and then they slowly with time they reduces. It goes towards more homogeneous solution, though some inhomogeneities persist. In phase, this is easy to see. This is in regime 2. So phases, it will produce sort of regions of opposite phases which will actually kill the superconductivity, the superconducting structure factor, as I said. And here it shows which are the modes which are picked up in the K space in the fast Brillouin zone. And then this was, of course, there was nothing. I have taken out the strong peak at k equals 0, the homogeneous mode, but otherwise you see it grows and then again decreases. So the similar, and this is in the inhomogeneities in the densities, and this is the current that I was talking about. So you can see some kind of a swirl in the current when the inhomogeneities, I mean strong instability comes up, At very large time, the current becomes very small puddles. They are sort of boring currents in small loops, but total current, as I said, in the system is zero. So again, having this current is something very different from what the homogeneous theories would have told you. Similar thing can be looked into in, this will be regime 1. So where the inhomogeneities are relatively weaker, and I will not talk about it. Similar structure, you can see there is a weak inhomogeneities, and that brings me to the conclusion slide. So spatially homogeneous post-quench superconducting state can become dynamically unstable to spatial fluctuation even in the absence of disorder in the Hamiltonian that is governing the dynamics. That's the main message. Onset of spatial instability is controlled by the interplay between temporal structure of homogeneous dynamics and response of finite wave vector modes. This is a long sentence. Don't worry, I mean, we basically talked about it. The resulting nonlinear spatiotemporal regimes are classified into regime 1 and regime 2 based on the dynamical behavior of the superconducting structure factor. And the unified framework is obtained, again, mistake. This is the problem of making slides at the very last moment, that connects homogeneous quench physics, instability, spontaneous structure formation, and all that. And finally, we hope that our results will extend to the existing understanding of the quench dynamics of superconductors. I thank you for your attention, and I just acknowledge once more to my collaborators, Medha Roychoudhury, Shankha Subra Bakshi, and Pinaki Mujumdar. I'll be happy to take questions.
We have time for one or two short questions.
So what are the length scales of these puddles or whatever, and how can they be imaged?
How can they be imaged? This you tell me. I don't know. Length scales, yeah. So this length scale should grow, and this is the part which is what I was sort of telling you at the beginning. So what happening is that there is some. So basically, it is like, then I probably should go back to the first slide, I mean, which is known for classical systems. So there are length scales which are, you start with some length scale, inherent length scale, and you go, then this puddles grow as the time grows, right? So, and this can go until infinity. I mean, if you think of this thing paramagnetic to ferromagnetic, at zero temperature, the puddle should grow to infinity. And at a finite temperature, what will happen in this case is that there will be some areas left out which are the size of thermal defects. So here, whether there will be defects, so now the point that I was trying to come to is that for our calculation, the system size and everything is limited for this quantum calculation, but you can roughly see that some phase is growing by reducing this phase. I mean, if you want to think that way. And then this is what is the, that's the sort of going towards the homogeneous phase given the system size. I can tell you the size of these, but these are not, I mean, we don't have enough control with the numerics to able to comment on how the length scale grows as a function of time, which is what people study in this thing. Classical, yeah.
Koshan, a quick question. So we know of thermal quench. Now, in this quantum quench where you have to change U, how do you think one will be able to realize that?
Realize in experiment? So this can be done, I mean, this has been done for this trap, this optical trap systems. Now, I don't see enough follow-up work to address everything from optical trap, but if you think a little bit more generally, so optical trap experiments are done for S-wave superconductor, which is what I am looking into. But otherwise, you can think of this pump probe because they are cousin for a theorist from experimental point of view, it's cousin because you can pump the system and then probe it at different time and see that. So now whether you can see these spatial structures, this again you are in a better position to tell me. I assume it's very difficult that you can't do STM while you are doing that, but what can be done? But I think it is better to look into something like if there is RMS current, that might be a little more easier, and that's one thing that we are calculating. So pump probe experiments are routinely done for high temperature superconductors. I have not seen many for low temperature cases, but that may be my limitation. I haven't searched enough.
Okay, so we don't have much time, so let's thank Professor Amit Goswami once again for this